Chapter 3, Part 6, Chair Conformations and Fun Facts about Alkanes. The chair conformation is the most stable conformation of cyclohexane. Every carbon atom is perfectly staggered and every bond angle is 109.5 degrees. There is movement but no rotation around the carbon-carbon sigma bonds. This is true for all cycloalkanes. Even though the bonds can still move and you can still get into different conformations, there's not going to be rotation around the sigma bonds because they are all linked together. But because of this lack of rotation, the relative positions of every hydrogen atom or other substituent that may be on the ring is locked in. So those relative cis and trans positions are always locked in no matter what conformation you're looking at. So let's take a look at the positions that exist on the cyclohexane chair conformation. So this is a chair, and this is a way of looking at cyclohexane. If we were to draw our flat ring, we are looking at cyclohexane from the side, and it's actually going to have this kind of 3D shape. So it's not actually, just this flat cyclohexane hexagon situation. I have a video where I use a modeling kit to actually show this better in 3D, and I'm including that in our video lectures list as well. So it should help you kind of understand what we're looking at. So if these are all of our carbons, and we're looking at the cyclohexane from the side, there are two locked in positions on a cyclohexane chair conformation. First, we're going to look at the axial positions. So because each of these carbons are perfectly tetrahedral, 109.5 degrees, these bond angles and positions are locked in. So axial positions are straight up and down, running through the molecule, and they alternate their up and down positions. So this one I drew pointing up from the ring. On the next carbon, I drew it pointing down. On the next carbon, the axial position is up. The next carbon, it's down. Next is up, and then the following one is down. So that's what I mean by they alternate on each carbon. Let me see if I can erase all these little circles I did. Now, the reason these positions are called axial is because they run up and down through the molecule, just like the axis of the Earth. Now, the other positions we have are called equatorial. The equatorial positions are at an angle, and they're always pointing the opposite direction of the axial position that exists on that carbon. So on this carbon, I drew the axial position up. That means that the equatorial position is going to be pointing down. On the next carbon, the axial position is pointing down, which means the equatorial is pointing up. So I'm going to alternate through my entire ring here. Now notice that a chair conformation is just a series of parallel lines. When you actually go to draw a chair on your own for the first time, you'll see that you draw these two parallel lines, and then you connect them, and then you connect those. And that's 3 series of parallel lines that you're just drawing. All of these positions, these axial and equatorial positions, are also parallel. So the axial ones are kind of obvious. They're actually all parallel to each other. But in the equatorial positions, they're parallel to the one that is opposite them in the ring. So we have pairs of parallel lines going through the ring. And these equatorial positions are opposite of the axial positions. I included one more chair here so that we could draw them all in the same molecule. So all of the axial positions go up and down. I always start in this corner or in any corner when I'm drawing a chair conformation, and the corner kind of points up, and that's my reminder that the axial position here is up. This corner kind of points down. That's my reminder that the axial position is down. And then once I have my bearings, I can just alternate throughout the entire ring. Now my equatorial position is always going to be opposite. this axial position is up, that means my equatorial position is down. And I'm going to alternate throughout the entire ring. So this does take practice to draw well. And I also want to point out that when students draw these, sometimes they kind of forget what it was supposed to look like, and you start drawing kind of chaotic things like this, which is neither axial nor equatorial, although maybe it was intended to be like equatorial up, which doesn't exist on this carbon. So be careful about drawing these, and if you mean for it to be axial, draw it straight up and down. And if you mean for it to be equatorial, make sure it's pointing in the correct direction and is clearly at an angle. I don't want to see any sort of like half-baked ideas like that. So the reason that these positions are locked in, again, I want to point out, is because that carbon-carbon rotation is limited. So on every carbon, there has to be an up and a down position, essentially. And they're going to be locked in at this 109.5 degree angle. And they're basically placeholders for the atoms that are attached to these carbons. So in cyclohexane, every single one of these sticks would have a hydrogen on it. A common type of question about chair conformations is, given a molecule that has stereochemistry, or rather like up and down bonds indicated for a substituted cyclohexane, provide the most stable or least stable cyclohexane conformation in a chair conformation. And the general rule that we want to follow when we're doing this is that we want to try to get either the biggest or the most substituents in the equatorial position. The most would be if there wasn't a clear biggest group, like you had just a bunch of methyl groups or they were all the same. The reason we want them in the equatorial position is something that's much easier to explain when I'm holding a modeling kit, and so I've provided a video where you can see that as well. It's easier to show in 3D because it's really dependent on the space that each bond has. But the equatorial positions, since they point out to the sides of the cyclohexane rather than pointing straight up and down through the cyclohexane, have much more space, and so they're just better places to put large things. So looking at this first example, there is an ethyl group, and the ethyl group is going to be our largest group. So we need to first draw a chair conformation. So there's one. Not my best work, but that's okay. And I think one of the sources of confusion for a lot of students is that it can be kind of difficult to figure out, where do I put this carbon? Does it go here? Does it go here? Does it go here? And it actually doesn't matter. What matters is that if I were to go clockwise, I have a methyl group, and then I have a blank carbon, and then I have an ethyl group, and then I have a methyl group. So as long as somewhere along your chair you are following that same clockwise pattern, you are totally fine to do this however you want. So what I tend to do is I try to look for a place where I can put whatever my equatorial thing is in the easiest equatorial position. So I have my largest group here, and this ethyl isn't much bigger than the methyl groups by any means. So I'd actually say it's kind of a toss-up with this example, whether the methyl group or the two methyls should actually be in the equatorial position. But let's go ahead and put the ethyl group in the equatorial position. So I'm going to look for a carbon that has an equatorial down position. So that would be this one, or this one. So let's put it here. This is equatorial down. So I've drawn this bond at an angle in my equatorial position, and that was this carbon. Now, clockwise from this carbon is a methyl that has to be pointing up. So if I go to my next carbon, that's this one, that position actually has an up that is equatorial. So my methyl group, which has to be up, is equatorial here. So that's actually pretty lucky. And then going 1, 2, 3 more carbons away. Oh, my methyl disappeared. Okay. I have another methyl group. So this one is directly opposite the ring from the other methyl group. So that's going to be this carbon. And I need this to be in an up position. And the up position here is actually axial. So this is the best conformation for this molecule because not only do I have the biggest group in the equatorial position, but I have 2 of the 3 groups in the equatorial position. Now, there is this concept called the chair flip, and I believe I have a slide on it coming up, but the chair flip is essentially, what if I had done this the opposite way? And typically you show your chair flip by drawing a chair that is slanting in the other direction. And in this circumstance, this methyl group that is axial would actually be equatorial, but it would still be up. So I would pick a carbon that has an equatorial up. And then across the ring from that would be my up methyl group, and that would be an axial position. And in between those, I would have an ethyl group pointing down, and that would also be axial. So this is the worst case scenario for this ring because I have 2 groups that are axial, and one of them is my biggest one. So this is the worst case scenario for this structure. But both of these conformations do exist, and because molecules are chaotic and they love a little entropy, they are constantly moving and going through some of these other conformations, even the ones that aren't favored. Okay, let's continue with our next example. I'm going to divide that out. So for my next example, I'm going to go ahead and draw my chair. So I'm going to move it over a little bit so that it doesn't get in the way of the other one. Oh, that's sloppy. Okay, let me try that again. Having a hard time with my pen being all weird. Okay. Close enough. So on this one, I have methyl up, bromine up, and methyl up. So if you're not sure how this is going to play out, you could try, putting a couple different things around the ring. Bromine is not really much larger than a methyl group or anything, so I would probably choose the methyl groups to be my up ones, plus I have 2 of them. So I'm going to look for a position where I can do an up equatorial. So that would be this carbon, or this carbon. And that's where I'm going to put my first methyl. So I'm going to do this one for fun. Oh, purple. I didn't know I selected that. So my methyl group is up. Now I'm going clockwise around my ring. That's this way. So on my next carbon, my up position happens to be axial. So that's where my bromine is going to live. And then next carbon over clockwise is my other methyl group, and I want that up, and that is going to be equatorial. So this is probably the best option for this molecule because I have 2 of my substituents pointing up in the equatorial position, and only 1 in the axial. Okay, last one. So methyl groups are significantly bigger than a hydroxyl group, so let's favor our methyl groups if we can. Now, the tricky thing is, with one of these methyl groups, if I put it equatorial, then the hydroxyl group can also be equatorial. But if I pick the wrong one to favor for equatorial, the hydroxyl group's actually going to end up axial. And since equatorial and axial positions alternate their ups and downs around the ring, I can actually go ahead and predict that ahead of time if I wanted to. So if this is equatorial down, then the up position here would be equatorial. The down position here would be equatorial. So that would make this hydroxyl group axial. And then these 2 are going to end up being the same because they are pointing in the same direction on carbons that are separated 1 apart. This is a pattern if you look around the chair. So this one would also be axial. So that's not the one that we want to pick. So if I make this one equatorial, then this will be equatorial as well, and the other methyl group will be axial. And if you can't plan that out in advance, that's totally okay. Just draw a chair and you can always change your answer if you don't like what you get. So here's my chair. And I want to put this group in my equatorial position. So I need an up equatorial position. I'm going to do that here just to change it up a little bit. So up equatorial, there's my methyl group. Going clockwise around the ring, 2 carbons away, is where my hydroxyl group is going to go. And that's also going to be equatorial because the up position here is equatorial. And then 2 carbons over, 1, 2. I need this methyl group to be pointing down. The down position on this carbon is axial. So this is the best possible structure for this cyclohexane. Okay, this image shows how these chair flips work. And again, if you want to see this in 3D, I also demonstrate this in my video. But when a chair flip occurs, everything that was axial becomes equatorial, and everything that was equatorial becomes axial. But the relative ups and downs stay the same. So I'm going to color code these carbons. This is my orange methyl, and I'll make this my purple methyl. In my next structure, this is my orange methyl, and this is my purple methyl. So you can see how the purple started off equatorial up, but now it's axial up. And it looks like I moved around the ring, but that's not what happened. It's just that if you try to draw up here, it would be axial. And that position should actually switch from axial to equatorial. So we have to draw it in a slightly different place in order to show that. So what was axial became equatorial, and what was equatorial became axial. So this example was cis 1,2-dimethyl cyclohexane, and because one of them has to be axial and one of them has to be equatorial, neither one of these is more stable than the other. They're actually completely equivalent. But for trans 1,2-dimethyl cyclohexane, where I have one group pointing up and one group pointing down, my options are to have both groups be axial or both groups equatorial. So there is a very significant difference in energy between these two. This one is much more energetically favored. It is lower energy and it is more stable by a lot. But notice that the relative up and down positions are staying the same, even though that axial and equatorial is flip-flopping. So this is our fun facts of alkanes portion of this slideshow. We're starting with the physical properties of alkanes. The main intermolecular force that alkanes experience is going to be your London dispersion forces. This means that they have fairly low intermolecular attraction, but as you increase the number of carbons and you increase that surface area, you will see increased dispersion forces, which means you're going to see higher melting and boiling points as well. In general, for alkanes, the boiling points tend to be low for the molecular weight. So an alkane that has a similar molecular weight to an alcohol is going to have a much lower boiling point than that alcohol of a similar weight, because alcohols have hydrogen bonding, they have polar forces. So those are going to have much higher boiling points than alkanes would. So because of this, when you have 1 to 4 carbons, so you're talking methane, ethane, propane, and butane, they tend to exist as gases unless you pressurize them and lower the temperature. 5 to 17 carbons exist as clear liquids. A lot of these can be found in gasoline. And 18 plus carbons exist as waxy solids. And a lot of these waxy solids can actually be dissolved in some of those lower carbon liquids, and you will also find some of those in gasoline as well. Let's talk reactions of alkanes. There's actually not a lot that you can do with alkanes. They are largely inert, meaning they're unreactive. And that's because they're comprised of nonpolar sigma bonds. There's just really no excess of electrons anywhere to initiate some chemistry. And there aren't any electropositive carbons to be a receptor of electrons. So there's just nothing really going on that would allow chemistry to occur. However, you can set them on fire. As mentioned, we have methane, ethane, propane, butane. All of these words are familiar to us because we've seen gases and we've seen lighters and things like that. So we know that we can light them on fire. I also mentioned that some of those higher weight alkanes are found in gasoline. So we know that we can set them on fire. Combustion is when you take something and you expose it to oxygen and fire, and you end up making carbon dioxide and water.